I'm Seth Shostak. I'm just going to make a quick introduction and then let them have at the subject. I did want to say something about this subject. Warp 8, Mr. Scott, will it happen? The future of space travel. When I was a grad student back before the Civil War, they brought some of the Star Trek writers to school, and a bunch of the students showed up, and one of the questions they asked the writers, they were asking about these funny years and stuff like that, but they asked the question of the writer, so how fast is Warp 1, Warp 2, Warp 3 anyhow? And the writer said, well, Warp 1 is the speed of light, and Warp 2 is the speed of light squared, and Warp 3 is the speed of light cubed. And so I was thinking, at what warp number are you going so fast you don't have time to slam on the brakes before you exit the galaxy? But that's because I was a dumb grad student. The undergrads, who were a lot smarter, pointed out something. They said, so what if I define the speed of light as 1 light year per year? So you're saying warp 2 is 1 times 1, and warp 3 is 1 times 1 times 1. And the guy threw up his hands and he said, look, man, I'm just a writer. Okay, to discuss this subject, we have from my right, from your left, from my right, yes. That's right, yeah, from my right to my further right. I'm going to say it's all right. Starting with Sean Carroll. Sean Carroll is a cosmologist and author of a book about the true nature of time down at, well, lovely Caltech, where this scenario took place, I might say. Next to Sean is Tim Russ, an actual alien Tuvok. He's a Vulcan. Tim Russ is not only a very accomplished actor and a director, but also an amateur astronomer. Next to Tim is Kevin Grazier. And Kevin, I've had the pleasure of being on panels with Kevin, and he's the real good. He's a Cassini scientist, studying Saturn, and also a sci-fi show consultant. And that's being modest, you'll hear more about that. And the fellow on the extreme there, this is Greg Papadopoulos. Greg Papadopoulos is a man of extraordinary accomplishment and insights in all sorts of things. And he's also a member of the SETI Institute's board of directors. So, without any further ado, I will suggest that you guys go, is this right? Beginning with Sean, I'm out of here, I've got to go do something else. These guys will keep you.
We'll let you know when we arrive.
Yeah, you'll arrive before I depart. That's the nature of faster than light travel.
All right, thanks, Seth. Admirable job filling in at the last second. So we're here to talk, I suppose, about whether or not it's possible to go faster than the speed of light, whether or not it ever will happen, and maybe we could talk about what you should do if it turns out that no, it is not actually possible. So the answer is no, it is not actually possible.
Thank you for coming.
Any questions? But it turns out that it's actually, let me just, is anyone going to disagree? Anyone going to have a plan? No, okay, so someone in the audience is going to have to nudge us a little bit. But let me emphasize that it's interesting the way in which it turns out to be very difficult or impossible to go faster than the speed of light. It's really, scientists, the people, the physicists who get paid the huge amounts of money to solve the equations, to think about these things, are not interested in being curmudgeonly and scolding and copy editors and saying, no, you can't do that. We would all love to be the person who said, oh no, here's the loophole that we didn't notice. And we take these possibilities very seriously. People write papers with lots of equations that appear in refereed journals discussing whether or not it would be possible somehow to go faster than the speed of light. And so far, the answer seems to be no. And I want to sort of indicate to you not only that it's so far, but there's good reasons to think it will continue that way. So you've all heard that this Einstein guy figured out that ordinary particles cannot go faster than the speed of light. But light can go at the speed of light. Something that's going slower, the moderator appears.
It's a concept
in some reference frame, he was on time.
It's a question of relativity.
It's
3 o'clock somewhere.
So if you take some particle moving more slowly than the speed of light and try to accelerate it, it requires an infinite amount of energy to go faster than light. And you think maybe you're done. But Einstein, being Einstein, didn't stop thinking. He kept on. And that result I just said is from special relativity. His idea of sort of the way, the kinematics of how things work without taking gravity into account. Then 10 years later, he comes up with general relativity, the theory of gravity, and he says that space and time are not just the stage on which the actors move, they're actors themselves. They have dynamics, they can move around, they respond to the forces, the energy, and the momentum, and the mass that other things have. In other words, you can bend space-time, which means you can bend what counts as the speed of light in one region of space compared to what it is in some other region of space. You can twist and warp space-time, and you can invent things that are given names like wormholes and warp drive and subway tubes that will take you across the galaxy in what to an external observer would be faster than the speed of light. The trick here is that you're never going faster than light. Light can always beat you, but you change the length of the path along which you're going. You change the geometry of space itself so that it takes just fewer light years to get from one point to another. This is, at least that possibility is opened up in general relativity. It's something we can contemplate. And then you go and check, all right, so if that happened, what would it require? What would be necessary to build a sort of space-time warping machine that for all intents and purposes would be like warp drive? And two things always go wrong. One is that you need negative energies to do it. You need to have a particle that weighs less than 0 when you put it on the scale. No such particles are known to exist. We don't know how to make that, so that's a problem. If you could do that, there's probably a bunch of things you would do before you would make warp drive. Let's put it that way. Technologically, there's a lot of possibilities that would open up if you could have negative energies. It might be possible, we don't know. There's no rule that is absolutely hard and fast against it, but it seems like an obstacle. The other thing is that if you can go faster than the speed of light, you can go backwards in time. This is more annoying, actually, than the negative energy thing. The negative energy thing, maybe that's a technology problem. The going backwards in time, the actual visiting your own past, seems like more than a technology problem. It seems at first like a logical problem, right? You can go kill your grandparents, buy stock in Microsoft or whatever you want to do. And that doesn't seem to happen in the real world. So scientists talk about it, they take it very seriously. They investigate ways to maybe make travel backwards in time logically possible, and that is conceivable. But we don't really have any framework for how the laws of physics would work in an absolutely consistent way if you could travel backwards and influence things in the past. So, in other words, try as we might to bend the laws that we know of physics as far as we can push them to make it possible for all intents and purposes to go faster than light, the universe seems to be resisting these thought experiments. We keep hitting obstacles. Every time we think we've figured out a loophole and a way around it, something shows up that says, no, that's actually not going to work. Now, that's not a logical proof against anything, but I think it's one of the reasons why most scientists, if you put your money where your mouth is, if you make a bet and say in the next 100 years we'll be going faster than the speed of light, at 100 to 1 odds, most of us are going to bet, no, we will not. He's done it, so I don't know. I mean, it might happen.
Hello, sorry I got here late. I did not find out until 5 minutes ago I was moderating this panel, but be that as it may, I guess I'll jump in. Kevin, I know that you worked most recently in the science fiction side of your life as the science consultant on Battlestar Galactica, and they had a somewhat different approach to traveling interstellar distances than what we did on Star Trek. Do you want to talk about that a little bit?
Sure. One of the most common questions I was asked at sci-fi conventions, as opposed to this, which is more of a science convention, was how the FTL drive in Galactica worked. And my response was a constant, I'm not going to answer that if it can be a plot point in a later episode. I'm not going to undermine one of our writers. How about it? No, and I'm serious. But now that it's out, and by the way, thank you for giving me the opportunity to plug my book coming out. On October 25th, The Science of Battlestar Galactica comes out. And they're actually, I was asked, okay, for internal house purposes, how does the FTL drive work? One of our writers, Bradley Thompson, contacted me. Actually, when I was arriving in Vancouver, I got a call. And he said, you knew this would happen eventually. We need you, we're rewriting episode 216. We need you to figure out how the FTL drive works, so we know what components it has, so we know it can get battle damaged, so in a last-minute Wrath of Khan-like maneuver, the captain can race down and save the ship and lose his life in the process. I said, Bradley, I've been up all night. He said, I get in tomorrow at 10:30. So for pacing of the room, and actually Ron Moore, our executive producer, had set out some constraints. We had the constraints of the term spinner that had been used several times in the show. We had the constraints of the special effects that you see on screen. So basically, between what Ron said and using all those things, I came up with an idea that's something similar to I guess it's the most similar in sci-fi would be the highliners from Dune. That you know, they call it folding space, and since space we believe can be warped, at least that's what our general relativity says, that gravity is a warping of space-time. The notion of galactic, this is the first time I've said this in publicly. It's in the book. Actually, it's in.
But still buy the book.
Still buy the book, yeah. The actual notes I submitted to Bradley that day actually appear in the book because they're kind of fun to read. But the way I envisioned it is that you have multiple field generators, that any one field generator can't itself generate enough warping to do this, but through the process of constructive interference, they create a field and they create a warping space where you literally compress between you and here, between where you are and where there is, to a point. You move, attach yourself to the opposite point, and then sling the shot out. So you're never really moving very far. You're just attaching yourself to a different part of space-time, and then when it snaps back, you're there. That was the notion of how the Galactus FTL drive worked. And so that was with, again, I had to take into mind the effects that we've already seen, the terminology we've already used, and the fact that we need to have something damaged that didn't entirely destroy our FTL, but that one person could fix. And in fact, what I said in the notes is that assume that if one of these four generators, field generators, is damaged, then either we don't jump or we jump to BFA. That would be a bum frack air alarm.
Now,
anyway, so that was the attempt to explain Galactica's FTL drive.
Now, in both of the scenarios that you guys have been discussing, warping space, folding space, however you want to describe it, as I understand it, the way that we think of these things today, it take a tremendous amount of energy to do this. Can you talk a little bit about that and the practicalities of, yeah, in principle, you can stretch space, you can compress it, but as a practical matter, what are the issues there? Sean, maybe you can start with that.
Well, that's a great question, but it's not a cut and dried question because we don't have technology, therefore we don't know precisely what it would be. Certain people have taken the proposals in the literature, in the scientific literature, that said, well, you could warp space and time in the following way, and just plugged in the numbers because physicists don't care how much energy it takes. That's an engineering problem. That would be solved, right? If there is some less than infinity amount of energy that would do it, we consider it a solved problem in our lives. So someone afterward went and plugged in how much energy it would take. The most respectable attempt at warp drive was done by Mexican physicist Miguel Alcubierre. And so someone plugged in his original solution, how much energy would it take to transport, a spaceship from one end of the galaxy to the other? It turns out to be many orders of magnitude larger than the total amount of energy in the observable universe. And so then the little project went on, so how can we, optimize it? And the best that I was able to find was that someone was able to show that you could move, an atom across the galaxy with only a few times the mass of the sun's worth of energy. And if you have the ability to harness the energy equal to the mass energy a few times the mass of the sun, there's nothing on the other side of the galaxy that's that interesting to you. I mean, you can do whatever you want right here. I mean, what is so necessary that you take that trip anyway? So the short version is, even in the scenarios where we allow ourselves anything, there would be practical considerations that you would need an awful lot of mass and energy.
And going back to a point you made earlier about there's always a gotcha, I think also people have done the modeling for, in the Alcubierre drive scenario, the modeling of what would occur within the warp bubble, and I believe it would achieve the temperature something in the order of 10 to 32 kelvins.
Yeah, that's hot.
Yeah.
Tim, speaking, is the only person on this panel who has actually piloted a starship.
Yes.
I'd like to throw this to you. There's also the question of navigation. How do we, here on the Earth, we've got now this wonderful system of GPS satellites that tells us where we are to within a few meters anywhere on the globe. Prior to that, of course, the big problem in navigation when people first started to venture out into the deep oceans was how to determine the longitude, and they needed clocks. You can tell your latitude by how far the pole star is above the horizon. Well, all of that stuff goes out the window when you're traveling through interstellar space. Do you recall some of the things that we described or talked about on Voyager and the other shows in terms of interstellar navigation? How do we find our way among the stars if we can actually get out there?
Yeah, we had on our console, we had a TomTom that was installed. It's several generations ahead of what we have now. It works quite well. And it was touchscreen, which is really cool.
Turn right
And
and
my buttons were flat, so I could really just touch them. You know, we didn't necessarily, usually on our show, there were issues with whatever we were using actually working properly. There was a lot of that. So whatever navigation we had was not working at the time because we were encountering something that was causing it not to work. But yeah, I think that we dealt more with a good deal with subspace and with the travel through to that kind of dimension more so than how we, you know, where the points of navigation were, because I think a lot of the time we get to our show is all taken for granted that we have that all dialed in.
Right.
But let me say this about, and I've been thinking about it. I was thinking about it over the last few months. If we had this panel during the time of Columbus, we were all sitting here dressed, you know, like they did at the time of Columbus. We wouldn't have microphones, but we would be sort of talking to the, you know, at the top of our voices in the panel. We would be discussing going to the moon, possibly, but all we would have at our disposal is wind power. And all of the wind power that was on planet Earth would not be able to get us to the moon. But that's because only 300 or 400 years ago, that's all the technology we had. So imagine 5,000 years from now, if our species can survive that without, you know, wiping ourselves out. To me, it's a question of Einstein's point of relativity. It is relative to now, relative to here. You touched upon it earlier about 100 years from now, perhaps not. But there is, in my opinion, no question that we have not discovered the means by which to do it. It's just that simple. We theorized about black holes not that long ago. Now we can create them in the lab for microseconds, but we are creating them. They were just a theory. We observed them. Now we can see them. We know where they are, and now we can create them. Now they're talking about multiple dimensions existing, multiple universes, and now seriously trying to discover and identify the proof of these things. Now, that's mind-boggling. Once you unlock that secret, what's on the other side of that door? And then the door behind that. And it may not be us, it may be robots that make that journey, but I think at some point in time, we're going to be doing it. And it's just a matter of when.
Well, I think that's a great point about the you know, what would somebody in the, you know, the 14th century, 13th century think about, you know, traveling to the moon? There was speculation that, you know, they had a very limited number of ways of thinking about that problem back then. And what we've seen in the 20th century and into the 21st now are these extraordinary explosions of technology, things that, you know, people couldn't imagine 100 years ago. I mentioned this morning during my talk that when I was growing up, I had a piano teacher who was a very elderly woman. She lived to be 104. She was 21 years old when the Wright brothers flew at Kitty Hawk, and she lived to see men walk on the moon. Charles Lindbergh, who was the first man to fly solo across the Atlantic, was at the launch of Apollo 11. He was only 66 years old. You know, it's astonishing. You know, we seem to have reached a bit of a plateau in space technology since those days, but that's also not uncommon in the development of technologies, and usually when you're at that plateau, it means that the time is kind of ripe for a breakthrough that nobody anticipated before, that takes you on to the next exponential development. And Greg, I wanted to ask you about this because you're a person with, you're a technologist, a person who worked for a company that is responsible for some extraordinary breakthroughs in technology that were rather exponential themselves. What do you think about this whole question of extrapolating into the future?
Well, it's a good one. I echo some of Tim's perspective on this because I'm an electrical engineer and computer architect by training. So in the middle of some pretty wicked exponentials right now, the phase change that we're going through, I'll mention that a bit. I want to take the conversation a little bit towards talking about bits versus talking about atoms for a while. But it turns out that the depressing thing is that they're probably the same, but I don't want to think about that. From a in our yes yeah exactly. So here I wanted to try to get you all to appreciate something about the speed of light, which sounds very fast. It's a foot per nanosecond is the way I think about them in designing things at sort of people scales. And a nanosecond is a billionth of a second. So if you have a gigahertz clock on your computer, then it's doing 1 billion pulses per second. So its wavelength, at most, in a vacuum, light goes that far. And to computer designers now, today, that's really slow. Speed of light is really, really slow. And because it actually turns out you build computers, the size of this room, and it is many clock, computer does something over here, and it's a long time before something, that actually effectively gets communicated across the room. So you see these kind of things that we think about galactic problems, you see it on a very small scale right now. I always ask my physicist friends to do one of two things to help me design faster computers, is either raise the speed of light, or give me another dimension I can stuff through. So I do want to just very briefly touch upon something, because we are in the middle of exponentials on information technology that, depending on how you think about it, my job has always been to try to predict the implications of these exponentials. The increase in computing power and memory and storage are such that, from my point of view, of course we will end up with silicon or whatever the electronic systems are. We'll end up with things that compute that are as good as we are, or faster, or whatever, however you want to look at it. And if you think about travel being more not us going somewhere, but sending information about us, encoding your DNA is it's less than a gigabyte, right? It fits on the flash card. Probably everything stored in your head is within a petabyte, like 1,000 terabytes. And so here's the exponential. This card will hold all of the brain contents of everyone in this room, right, in 30 years. And, anybody want to climb aboard and, go on this? So I've always...
Just don't stick me in a side.
Right, yeah, yes. Okay, so to finally wrap this up, of course, I would love to see communications faster than the speed of light, maybe hoping that, if there's any chink that we can drive through on this, will be in this area. But as I said, unfortunately, in this way, it actually turns out maybe bits and atoms are the same thing, so, or at least duals. So Einstein also says you can't communicate faster than the speed of light. That's
true enough. All right, well, let's open it up to questions. We seem to have a lot of them already out there. The gentleman in the sort of purplish shirt.
This topic was billed as space travel in the future, and you spent a lot of time telling us about what's not going to work and what's wrong with the theories that we have in fiction. Can you spend some time now telling us about what are the possibilities that are being looked at seriously for space travel?
That's a great question. And why don't we focus on interstellar, like the near-term interstellar robotic kind of stuff? Because I think we have a pretty good idea of the. Well, we could do interplanetary too, but I think interstellar. I know that there are some ideas for solar sails and microgram spacecraft. Maybe you guys can talk a little bit about that.
Actually, let me do the reverse. Let me start about within the solar system and then work out to the interstellar. Within the solar system, we've been using chemical rockets for years, and more to the point, what has been kind of overlooked is we've been using chemical rockets and gravity assist. Because with chemical rockets that we have today, much of the solar system is inaccessible, to be quite honest. The rockets we build today, we can't get to most of the solar system unless we do gravity assist around the planet. So we really use a combination of the planet's gravity and chemical rockets right now to put our spacecraft wherever we need them to be. A good example of a spacecraft on which I work is Cassini, and Cassini needed the gravity of Venus twice, Earth, and then Jupiter to get to Saturn, in addition to a Titan IV Bravo booster. Now that said, we've been going to ion engines in some of our more recent spacecraft. There was a spacecraft called Deep Space One that was a technology proving mission. It rendezvoused with a comet and an asteroid, but some missions we do are designed to prove technology, and any science return is considered to be a bonus. Well, we've been using ion engines for years, for decades, Actually, they've been a stalwart of science fiction for 50 years. Remember, in the original Star Trek, they followed the ion trail to recover Spock's brain. Brain and brain, what is brain? And they,
Yes, I do.
yeah, they've been using this ion engine as station keeping for Earth orbiting satellites for decades, meaning that communication satellites, weather satellites that are in geostationary orbit tend to drift because the Earth's gravitational field isn't uniform, and to keep them in place to station keep, they use these little ion engines. Now, Deep Space One being the first, Smart One being another, and currently the Dawn spacecraft en route to the asteroid Ceres and Vesta are using these ion engines. And what an ion engine is essentially a linear accelerator. You have a container full of xenon, which is an inert gas, which means it won't react with your containment vessel, and it also is easily ionized. So you strip off an outer electron, accelerate it through a linear accelerator, and then basically a constant stream of ion going out your tailpipe is what propels your spacecraft. Now from a thrust standpoint, an ion engine produces about as much thrust as the weight of this piece of paper in my hand, which may make you initially say, well, that's not going to get you anywhere quickly. And you're right, it's not going to get you anywhere quickly in the short term. But long term, these ion engines actually have a very high specific impulse, a variable we use to measure the efficiency of thrust. And if you wait a while, if you're going somewhere a little more distant, these ion engines are extremely efficient and can get you up to pretty high speeds, because even though you only have thrust of a piece of paper, you're thrusting for months at a time. You see, someone sees the efficiency of that, just had a breakthrough. That's your next propulsion breakthrough right there. Now, that said, that's probably not going to get you to the next star system. And people have looked in the past at different ways of doing that. In fact, there was a form of nuclear pulse technology, basically you light up a nuke behind your spacecraft, and the combination of the photon pressure and the fact that you vaporize part of a plate and the material flying off from that can actually propel a spacecraft. Successful experiments were done on this in the 60s on this nuclear pulse propulsion with conventional weapons, but it could never be scaled up to actually nuclear pulse because, number one, the EMP generated, and that in space is not good when you basically shut down everybody's television and computer and everything electronic for over the entire continent, which a nuke in space would do if close enough to the Earth. But again, given the sensitivities for lighting off the nuke back when this was done, so it was never taken beyond chemical weapons. But there are nuclear pulse technology and plasma technologies that could accelerate us to pretty high rates of speed. What hasn't been mentioned is when we talk about Einstein relativity, I was mentioning this to Sean earlier, that for a show called Virtuality that I worked on, it was only a pilot, I don't know if anybody saw it, it was a show that probably should have flew and didn't, but we actually, we tried to take into account relativity, and we had to, I had to find a star system that we could get to round trip under the speed of light in 10 years. Well, using relativity, it turns out that you can, there's some tricks involved, and it turns out that if you travel at square root of 2/2 times the speed of light, which is about 0.71 times the speed of light, the people in the spacecraft are functionally traveling at the speed of light, meaning that it would take 4.3 years to get to Alpha Centauri. Now, when the rest frame back on Earth, it would be much longer. But so then you have that whole game you have to deal with playing. And I've prattled on like a really long time. I'm not that interesting. I'll leave it over to Sean to continue on, or someone else to.
Yeah, actually, I do want to sort of address your question in a tangential way, starting from what Tim said about the difficulty in extrapolating technology into the future. I completely agree that it is extremely difficult to make sensible statements about what technology will be able to do 5,000 years from now or even 100 years from now. I nevertheless disagree that therefore we will travel faster than the speed of light. I think that's a law of physics. But it's illustrative of why it's difficult to extrapolate technology into the future. We're really good at taking the technology we have now and imagining that it is better. So we have rockets and we have airplanes and we have things like that. It's easy to imagine that they're going faster. What's harder is to imagine completely different kinds of technology. 50 years ago, if you asked people to extrapolate to today, you would have heard a lot about jetpacks and flying cars. You would not have heard about the internet and cell phones. It's a different kind of thing. And so it might very well be that the question of realistic travel to the stars or very far away is the wrong question to ask. If you think about what are the realistic technologies that are going to be changing our world in dramatic ways over the 100-year time scale, my first bet would be immortality. There's nothing conceptually difficult about stopping human bodies from aging. Probably at the even money level, no one in this room will live forever, but I can't say that about your grandkids. This is something people are working on, and it's kind of possible. Likewise, robots, which were mentioned, artificial intelligence is getting better, and the thing to take into mind is that the difference, the dividing line between what is a robot and what is a living thing is going to get fuzzier. We'll become more robot-like, robots will become more human-like. It might be that what we send to the stars is in some way a robot, in some way a human being, in some way halfway in between. It might be that we lose interest in going to the stars because we create our own virtual environments, we all get uploaded into the matrix. I'm not saying that that's true, but I'm saying is this is how difficult it is. We don't even know what are the right questions to ask about anything beyond 100 years from now.
Yeah, and what about if we, and I was just thinking, you mentioned it, like I said, I didn't bring it up at the time, but yes, our form will change. Our corporeal bodies will no longer be what the standard is. If we are able to download our consciousness into a form of energy. The radio waves travel at the speed of light. So if you're able to beam yourself across the universe, as it were, even that still takes a while. At the closest stars at 4 years, that's still a long time traveling.
But you don't feel any time passing.
Objectively.
True, it's true. Yeah, but that is a way in which that could be done. And I think you're absolutely right, and I believe it as well, that kind of technology is in the future. There is nothing, I don't think there's anything we could even imagine as sci-fi writers and creators that will not eventually, again, if we survive as a species, our future lies out in space. We have to move into space.
Going back to what Sean said about the human and the mechanical merging and what implications for exploration, am I the only person who has a problem with the notion that the first explorer of Alpha Centauri is a toaster? That's a Battlestar Galactica line.
You, sir.
Thank you. It was sort of maybe the point I wasn't making very carefully about or clearly about, what just happens in 30 years in terms of this ability I think upload or be able to certainly reproduce what's in your head somewhere else. I see completely consistent with things like what you're talking about.
And I think there's an implication of what Sean said, is as far as the longevity issue, it may obviate the need to travel FTL. Is that what you're implying? Or?
No, I'm just saying we don't know. That's the safest possible thing you can say on these
In terms
things.
of what, yeah.
These people think they know.
Gentleman in the white t-shirt, you got a question?
Thank you. The Japanese have a freezer which is also a microwave. And it's a vitrification device which is used in the science of reviving frozen mammals. And I'm wondering if there are any other combinations of household appliances which you think might be useful.
Yeah.
I certainly wouldn't want to be on the microwave end of that deal. That sounds like a jolly way to go.
Gosh, it's a toaster oven, convection oven, blenders would be good. Yes. You're soaking in it. This gentleman.
You mentioned the ion drive, which generates enough to lift a piece of paper. And of course, that doesn't get you into orbit at all.
No, it doesn't.
Is anybody seriously looking at the Arthur Clarke's idea of the space elevator? Because it takes a huge amount of energy to build one, but then it just returns over and over again, and pretty soon it's free.
Ever read Red Mars?
Yeah.
End of conversation.
The failure mode's not pretty.
For those of us who have not read it. Yeah.
For those of us who have not read it, basically there's a space elevator on Mars that gets deorbited, and as it wraps around Mars at several times the speed of sound as it impacts, it's just ugly and a half.
But the question is, yes, people take space elevator construction seriously.
They do actually, but I think that they do, and they look at carbon composites and nanomaterials to build the thing, and they probably could, from a conceptual level, actually build one. Actual implementation, I think, might meet some resistance.
You, sir, the glasses dark hair. Yeah.
Is anybody still doing research on things like nuclear saltwater rockets or open cycle engines?
The question was about nuclear propulsion, nuclear saltwater, open cycle.
I do know they were looking at, for a Jupiter mission, they were looking at nuclear electric propulsion. That's, you know, the ion engines that are on Dawn, SMART, and Deep Space One were propelled, the power source were solar panels. And for deep space, they're looking at nuclear propulsion, where the power source to drive your linear accelerator is an RTG, the same thing that we use on things like Cassini. As far as other forms of nuclear propulsion, I am unaware of any efforts at present.
Some of you may know that in the 1960s, the United States built and tested a nuclear thermal rocket called NERVA. We spent a couple of $1 billion on it, did ground tests, never put it in orbit. You know, the technology, in effect, it exists, but the political will, the desire to use it is a different question.
How much speed, how much greater speed is that?
Well, it's twice the specific impulse, typically, so it's about twice as efficient as a chemical rocket. So for, you know, much less expenditure of fuel, you can get to your destination somewhat more quickly. Cool. You, sir.
Yeah, just two questions. One of them, you talk a little bit about the light sail possibilities. And the other is the whole issue of, some people have written some books about the hazards of space travel, and there's like 10 of them, and the longer you're in space, the more hazardous it is. And so just, and then it's more than just an engineering problem.
Yes.
Well, some of the effects you have from space travel are time dependent, and some aren't. You're like bone decalcification. When you go up in space, you lose about 5% of your bone mass. You don't ever get back. And that seems to be somewhat independent of how long you're up there. So some of these things are independent, but as far as radiation exposure, yeah, the longer you're up there, the more you're going to get, unless you've got a heavily shielded spacecraft. And then you get the problem with, you know, it takes about 100 pounds of rocket fuel, rough ballpark, 100 pounds of rocket fuel to get a pound into low Earth orbit, just in low Earth orbit. So if you're putting up heavy shielding, that's expensive. And, you know, so you can shield against some of these things, like the radiation exposure, but it comes at an extreme cost. I don't know. I'm really on.
Oh, well, I was just going to add that, yeah, that is something that is somewhat underappreciated by a lot of people who speculate about the future of space travel. Not only is you know, the microgravity environment very deleterious for human beings, and bone loss, bone mass loss, muscle mass loss, the exposure to radiation. Obviously, when you get beyond our Van Allen belts out in interplanetary space, and how do you shield against that? There's psychological factors. Getting onto Mars once you've survived all of that. We don't know enough about the Martian environment right now to even know how to protect astronauts on the surface of Mars. How do we protect them against the very fine dust and regolith and some of this stuff that, you know, will get into everything, even if you're there for just a few hours. You know, it's a huge problem. And propulsion is kind of the easiest part of this equation. I think these other factors are going to be far more difficult. That's my opinion. I'm not an expert in the field, but just from what I understand about the kinds of things that people are dealing with in terms of making this sort of thing practical, the propulsion is probably the easiest part of the equation, or at least the part we understand best.
As far as getting to the inner solar system of Mars and the life for colonization, and I think wouldn't it make sense? I mean, if you were colonizing Mars, as we are now, would it be perhaps it would make sense to go underground once you're on the surface,
Absolutely.
To live underground permanently, because then you're shielded from radiation. Plus you're in the
Mars
elements.
has no atmosphere to shield you against. Well, it has
Yes.
a very thin atmosphere, not enough to shield you against a lot of cosmic rays. When there's a coronal mass ejection, an event on the sun that happens to be aimed in Mars' direction, you would not want to be standing on the surface of Mars in a spacesuit when something like that happens. It has no magnetic field to speak of, so a lot of different issues that come into play beyond just how fast can you make the spaceship.
And not only that, Mars has no oxygen in the atmosphere, and it's a variant of oxygen, which is ozone, which protects us from the UV radiation of the sun. So even though Mars is 1.5 times away from the Earth as the sun is Earth, it gets about half the overall radiation. But having that said, it gets way more ultraviolet radiation on the surface constantly because of the no ozone layer. So you have to protect against that as a constant influx of UV radiation. So there's that issue that going underground would pretty much address.
Yeah.
Doug, you had a question.
Are you guys familiar with the Bessemer rocket, and I'd like your opinions on whether that's going to really, if you think that's a feasible way of getting to Mars and other places faster.
The Bessemer rocket, that's Franklin Chang Diaz is. You're familiar with it?
Yeah, actually, I alluded to it earlier. I mentioned various forms of plasma. Yeah, but I don't know what the state of that is. So I'm familiar with it, but I don't know what the current state of it. They're doing any experiments with that.
But the last I heard, they're moving forward. They've done some tests with I think a 100 kilowatt generator, and they want to put one up on the space station in 2 or 3 years and test it on orbit. So, you know, everybody thinks it's not a new idea necessarily, and it's something that, you know, again, it's a question of how long is it going to take to engineer something that actually works, and that may be as good as or even better than some kind of nuclear thermal or nuclear electric. But even in his scenarios, I think that to really get something big enough to send people to Mars, you would need a small, you know, a nuclear fission energy source to generate the amount of electricity this system needs. So, you know, you still kind of have a nuclear dimension.
Just a small comment. NASA has a prize for developing tethers that would allow space elevators to occur. And they just had an event in Seattle this week on that. And there was also a space elevator games that took place in Tokyo earlier in the week.
Yeah, people are definitely, you know, investing in it, spending money. It's one of those things that, you know, it's very much a long shot, but, you know, if it pays off big. So, let's see, who am I not? You, sir, yes.
Well, it seems like there's a vision of sending people in big ships. What about research on sending smaller ships? I mean, the Mars rovers are just a spectacular success.
Yeah.
Why don't we send 1,000 little tiny ones, and each of us would be virtually linked to that thing? We could map the whole planet and talk to each other down here. Nobody's in any danger at all.
I thought you were going to say, what if we were sending a midget? I actually thought, I pitched an idea very many years ago as kind of a joke that you get a little person, a small person, you put him in a coma. You know, you induce a coma medically, you put him on a ship, you know, it needs to be only half the size of a Mercury capsule. You know, if you're interested in conserving resources, there are a lot of creative solutions, but they're not politically acceptable.
So
I do like the, I'm sorry?
Are any little rovers being designed?
Sure, yeah, who can speak to that?
Like I said, you know, mass is always the issue in space, and then the smaller, the better. So yeah, there's always been a drive to make things smaller. You know, you heard the whole mantra of the 90s, smaller, faster, cheaper. Engineers used to say, take two. But besides that, yeah, the goal was to make smaller missions less expensive, and the pain of losing one is much less. So more missions, you know, and as technology becomes you know, improves, the sensors and get better and the mass goes down. It may seem counterintuitive at first, but spacecraft designers don't like high tech. I mean, I guess they don't like high tech, that's going to be an overgeneralization. But they're averse to the latest and greatest because they want proven and something they know is going to work because of the implications of, you know, in taxpayer dollars of a mission failure. So they want something that's going to work, you know, every single time. So like the instrument on which I work is a 1024 by 1024 CCD. It's a 1 megapixel CCD. At the time that was launched, that was considered to be pretty high tech. Now you can go to Walmart and top that. So yes, the answer is people are trying to make things smaller, less massive, and more of them. That said, the next rover going to Mars is MSL, and that is roughly the size of a Mini Cooper.
It's bigger, but it's awesome. If you see, I saw a mock about you. We gotta send this. There's just no way. But there is a justification for it. I mean, how many times have you seen news reports about a satellite, either a lander or in orbit, sort of analyzes some facets of one of the other planets or moons in the solar system and comes back and says, we've looked for life, and there's some hints there, but we're not sure. And part of this, you know, you need to build better technology, you know, more elaborate laboratories to send there. One thing is mapping, and that we can do. But you want to build a better chemistry set and send it there if you really want to understand better what you found. You would like to do more than just plant the flag and make a map. You actually want to analyze and do some experiments. And ultimately, that's a good reason for building something more substantial.
Gentleman, blonde hair and glasses, white t-shirt.
Yeah,
I have a question for Sean. I'm a physicist and also a Star Trek fan, by the way. This is about a satire of Spock's brain. So, but anyway, you know, if you look at the, I was wondering if I could get you to admit, if you look at the history of physics, you know, there was Newton's laws and Einstein's laws. So if you compare what we knew back then and then relate it to what Tim was saying in 5,000 years, in 5,000 years, could there be, you know, some new discovery about the laws of physics that maybe, you know, we can go faster than the speed of light somehow?
Yeah, we talked about it earlier. It was just a matter. He was saying we're speculating. You know, we can speculate all day, but you can't project ourselves into the future, but the possibilities.
You can't say for sure that, you know, that's ultimate.
No,
If there's ever a question that says, as a physicist, can you guarantee for sure that the following is true? The answer is always no. I never can guarantee for sure. But what I'm saying is that it is nevertheless important to keep clear in your mind the distinction between a technology problem and a laws of physics problem. If there's a technology problem, you know, how can we get to Mars? That sounds hard. How can we send a generation ship to Alpha Centauri or across the galaxy? That sounds hard. How could we harness the amount of energy in an entire star? That sounds hard. But none of these are against the laws of physics. They're just hard. Traveling faster than the speed of light, as far as we can tell, is against the laws of physics. So it is, unless the laws of physics change in some way, we're not going to be able to find a technological breakthrough that gets us faster than the speed of light. I can't guarantee you that that change in our understanding of laws of physics will not happen, but I would bet against it personally.
Every time you say nothing can go faster than light, if it's physical, what is with information? I remember there are quantum mechanics, if two particles meet in each other and go away from and are on different sides of the galaxy, and something happens to one, you can, it really happens with the others. Without that it needs time. Is there any way to find ways to communicate faster than light? It will be very easy, for example, to manage the Pathfinder mission on Mars if you don't have to wait 8 minutes to bring to a new position, for example. Is something possible in this direction?
Sure. So the question is, forgetting about sending stuff, particles, mass, faster than the speed of light, if we think about sending information faster than the speed of light, and we take into account what we know about the spooky effects of quantum mechanics and entanglement, could we somehow get signals or some form of information to move faster than the speed of light? And the answer is no. And this is, it's again, it's a subtle reason why no. You have, what the lesson of entanglement is that you take two particles and they have some property, yes, no, and one is yes and one is no. It might be, you know, are they spinning clockwise or counterclockwise? And what quantum mechanics says is that they can be in a state where you don't know whether particle A is yes or no. You don't know whether particle B is yes or no, but you know that they're in opposite states. You know that if one of them is yes, the other one is no. That's how quantum mechanics works. And then you arrange them this way, but you need to arrange them here, okay? And then you need to send one of them very, very far away, and that takes time because you're sending a particle more slowly than the speed of light. And then quantum mechanics says if you observe one of these particles, and is it yes or is it no? As soon as you observe it, you know with 100% certainty that the other one is the opposite. However, they don't know what you observed. So no information has passed. I observed the particle and it was yes or it was no, but the person a light year away doesn't know what I observed. What quantum mechanics says is that if we both then come together by hopping in our spaceships and moving slower than the speed of light, we will compare the results of our observations and they will be compatible with each other. But there's no way to send a signal. In fact, there are theorems that show that as far as quantum mechanics is concerned, you cannot actually send signals, send information, send useful data faster than the speed of light.
I find that very depressing.
You mentioned earlier, and you said the same thing, we don't know about the laws of physics. Absolutely right. We don't know if the laws of physics are going to change or not. But we are in agreement that scientists, physicists now, are seriously discussing parallel universes and multiple universes as we speak. Is that correct?
Oh, yeah.
They are seriously physicists, not somebody off the, Jerry Springer. Physicists are talking about multiple universes, multiple dimensional planes the universe having more than one plane, more than one dimension, etc., parallel universes, and the next step, the very next step, as we know physicists and scientists, is going to be to prove that they exist, and the step after that is how do we use it. Once we break that down, and it will happen, we won't be alive. I think everybody in this room may not be alive, I don't know, but the bottom line is that, to me, it seems to me, that will be the breakthrough, because then you're leaving with an entirely different kind of universe. Once you learn how to manipulate that universe, that to me is mind-boggling. I don't know how else to describe it. That to me seems like the key, more so than the speed of light or anything else we have. Multiple universes, how they work, are they intersecting, how can you travel from one to the other? That's going to be the next thing. It's not going to be, oh, we found, that's how, okay, fine, and we got to go up to something. No. That breakthrough will be bigger than anything we've ever, unless, like, you guys disagree, it was going to be the biggest thing in science we could ever discover. Multiple universes.
The gentleman at the end of the third row.
I'm troubled by what I think is one little thing about the way science works. If I can think of one mode over here of experimental and observation, another mode over here of theory, we can start at either path. We can generate a theory, we can go over here and test it to see if it fits. If we can experiment, measure something, or we observe something, does it match up? Then we can go back and say, okay, we see something or we observe something, can we go over to the other world and see if we can match it up with a theory? Does the theory predict something new that we didn't know before? We'll look for it. If we match it up, it's a good theory, we'll keep it. And we can maybe cook up a model like Schrodinger's equation or an electron or something like that that says, okay, we can explain this thing. We can test it with electronic fields or whatever, and we think the theory is good. So we're trying to make models of what's out there. It's a thought experiment, and it's a measurement experiment. We have measurement errors, we have observation errors, we have theory errors. We're generating this as a picture of the universe, we think. It's our model in our head in both cases. But we have errors in here, and we learn things as we keep refining the model of science. That's the way science works, in my opinion. Now, do you agree with any of this?
Sounds reasonable to me.
Sure. I mean, I would just emphasize. There's sometimes, I'm not saying that you're advocating this point of view, but sometimes scientists get accused of being establishmentarianist. They're defending the common conventional wisdom. And the truth is, every scientist would love nothing more than to show that everyone else was wrong. That's how you make money, right, in science. Einstein did not, prop up Newton. He said, no, Newton was wrong. We can come up with something better. So if we do push ideas like there's a speed limit to the universe, that there's stuff called dark matter, that there's stuff called quantum entanglement, it's because those are the ideas that best fit the observations that we have. And if anyone can come up with a better idea that proves more using less, we will be on it like that.
Okay, one final question, the gentleman in the white shirt, yes.
For Sean, I was wondering if you think the newer wormhole metrics that satisfy the quantum inequalities and appear to use very little exotic matter, if they represent any progress from, say, Morris and Thorne or some of the older ones.
Are you getting at that they represent what?
Progress from, Morris and Thorne.
Oh yeah, sure. Well, I'll try to repeat the question. Tell me if I'm accurate or not. We alluded before to ideas about warp drive and other ideas within the context of Einstein's general relativity, where you're changing the geometry, the dynamics of space and time, in order to get someplace faster than you otherwise would have. And what has happened is that this has gone in the last 10, 20 years from, if you had asked someone who was an expert in general relativity, they would say, yeah, I don't know, maybe that's possible, I'm not really sure. Now we've written down the equations. We know exact, precise examples of when this could work. And so, given these precise examples, we can start asking questions about them, like how much energy would it take? Do you need to violate energy conditions? Do you need negative energies? Can quantum mechanics help you, etc., and so forth? And the question, I guess, is how much progress does this represent, in some sense? And yeah, no, this absolutely represents progress because, We don't like to just say you can't do something. We like to say, here's what goes wrong. And the reason why we like to do that is because then you can say, well, maybe I'll tweak this little button and it will not go wrong anymore, and you can fix things. And that's why I'm very reluctant to say, with anything like absolute certainty, that we won't come up with a way to sneak around the galaxy in a very short period of time. I doubt that it will work. I would bet against it because the examples that you're referring to all have pathologies, one way or another. There's always something that goes wrong with them. It seems as if, you're beating your head against the wall, maybe the wall is just kind of hard, and maybe you're not going to break through it. That doesn't mean we should stop. We should understand as well as we can what is possible and what is not possible. I would love a general theorem, a general no warp drive theorem. Under these assumptions, you cannot effectively travel faster than the speed of light. We don't have that, and right now these examples are the best we can do.
All right, well, on that somewhat optimistic note, maybe, I want to thank everybody for participating.
Thank you.